Multivariable finite difference method. We're going to introduce a very strange concept in this video called a staggered grid. And very often when we have multiple functions, in order to write the finite differences as compactly and accurately as possible, we're going to stagger where those functions are defined on our grid. So we'll talk about that. And then we'll have to talk about what happens to our derivative matrices on a staggered grid because something interesting happens there as well. Then I'll step you through an example. Staggered grid. So let's say we have a very basic multivariable problem. We have two differential equations and we have two functions. We have an unknown function f and an unknown function g. How would we even approach this? Well, let's just make a guess. Let's approximate this with finite differences. So we have correct finite differences on the left. We'll have our function at the function at the next cell minus the function at the previous cell. And the spacing between those points is 2 delta x. So we divide by 2 delta x and we get slope or our first order derivative. And of course that equals a times gx. We'll do the same thing for the second equation. And let's look at that. Does this work? Are we there? And the answer is yes, this would work, and we're there sort of. But think about this finite difference. We are actually spanning this grid by a distance of 2 delta x. And the farther out on the grid you reach to calculate your finite differences, the less accurate it will be. Now, maybe this is the only choice we have, in which case, well, that's all we can do. But it turns out there's something better we can do in this case where we only have to reach 1 delta x. And so if those function values are tighter against where we're calculating that finite difference, that will improve our accuracy. So let's not make the spacing 2 delta x. Let's make it delta x. Okay, so now we have our function at x plus delta x over 2 minus f at x minus delta x over 2. And so the spacing between those points is only a single delta x. And we do the same thing for g. So we've tightened up our finite differences and we should be here. So let's think about this. Are we here? Is this a good formulation for our finite differences? Well, it turns out no. And that's because we have to somehow evaluate our function at the midpoint. We're probably only going to know this at integer multiples of delta x. And now suddenly we have to know this at these half steps for both f and g. And well, to even do that, we'd have to think about interpolations and the complexity of our equations explodes. So this is not really a good answer, I don't think. Okay, so let's only use f and g where they're defined. Let's tighten up those finite differences so they only span 1 delta x, and we're ending up here. So we have our function at x plus delta x minus f at x. So the distance between those points is only 1 delta x, so we divide by 1 delta x, and then equals agx, and we do a similar thing for our second equation. So we fixed everything. We only have our functions at our discrete multiples of delta x. We're only spanning a single delta x. Is this a good formulation? And it turns out not. We are breaking a very serious rule here. We have to go through our finite difference equation and we have to inspect every single term. We need to make sure that every single term is defined at the same point. And I'll normally say that the finite differences have to be at the same point in time and space. We don't have time here, we only have space. So that's where we're looking. And so these finite differences are actually defined at x plus delta x divided by 2, whereas g of x is happening at x. And so this equation doesn't work. Now, sometimes we can get away with this, and there are times where we will do this, but that's not a good thing to do here. In general, we want nice, tight, finite differences, and we want each term defined at the same point, or our codes could go unstable. So what do we do? Well, now let's talk about this staggered grid. What if we define f to exist at the integer steps of delta x? So we have now a finite difference, f at x plus delta x minus f of x over delta x. That's a fine finite difference, but this finite difference is calculating a derivative at x plus delta x divided by 2. What if that's where we defined where g exists? Then this whole equation would work just fine. Then down here, since g is existing at the sort of half steps, we have a g at x plus delta x over 2 minus g at x minus delta x over 2. This still only spans a single delta x. The midpoint between that is x, which is right where f is defined. And that's exactly what we do. So this is good. We have nice tight finite differences. They're staggered, but all terms in the equations exist at the same point in space. And the only drawback really to this is that we have to remember that f and g are at physically different points. So when we start doing things like assigning material properties, even though f and g might be within the same cell on the grid, if our device sort of slices through the middle of that, f and g could end up one inside and one outside. So we just have to treat them as being in physically different locations and remember that, and that's the only drawback. Otherwise, our finite differences are very compact and very accurate. So this is what we will do. Now to draw this on a grid, we have our first cell that would start right around here, and it would end here, but not actually include, this point exists at the edge of the cell, but it's really associated with the next cell. So we have f defined right at the start of the cell and g defined at the middle of the cell. And so if we're ever wanting a derivative at g, if we're taking derivative of f, we're looking at the finite difference between these two values and interpreting that as a central finite difference that exists at the middle. Likewise, when we're calculating the derivative of g and we're using a finite difference, we interpret that as a central finite difference that exists at the midpoint, right where f is. So this staggered grid works really well for us. Just as sort of an aside, this is something that I do all the time in electromagnetic simulations. And if I'm doing a three-dimensional electromagnetic simulation, I actually have 6 functions happening at the same time. I have electric and magnetic fields, and each of those have x, y, and z components. So altogether, that's 6 functions. And in a three-dimensional setting, they're staggered this way. And this staggering was developed by a scientist, Dr. Kane Yee. And so this is now called the Yee grid, and the algorithm, the Yee grid scheme, or the Yee scheme. So a very famous person now. So I don't like to write my finite difference equations in terms of x plus delta x and all that. That kind of gives us some physical meaning to talk about the equations. But the reality is we're working with arrays in computer memory, and I much prefer to work in terms of array indices. So writing our finite difference approximations in terms of array indices, we are here. So what we have to remember is that f sub 1 and g sub 1, while they're in the same cell in the grid, they're in physically different places. So f sub I and g sub I, we just have to remember it's staggered, they're offset by a half cell. So our first differential equation, we have f at the next cell minus f in the I cell divided by delta x equals a gi. Down here, the finite difference looks a little bit different. Now it's g in the same cell minus g from the previous cell divided by delta x is b times fi. Let's look at that on the grid. So let's say we would like to take the derivative of f, and that finite difference will exist at the midpoint. So it's f from the next cell minus f from the previous cell divided by the spacing delta x. Now, likewise, if we would like to calculate the derivative of g, let's say we want that derivative right here. So in this case, it's going to be g from the same cell as this f minus g from the previous cell. So due to the staggering, these finite differences are written a little bit differently. And it turns out when we get to the derivative matrices, we will have different derivative matrices, whether we're calculating the derivative for f or the derivative for g. Those derivative matrices, turns out, will be related, and we'll get to that. Derivative matrices for staggered grids. So we have a grid, And what we want to do, in this case, we have a 5-cell grid. We want to write both of our finite difference equations once for each cell in the grid. So this means we'll end up with 10 equations. So our first finite difference equation gives us 5 equations. And of course, that last equation is trying to access an F6, right? Because we need a derivative on top of G5, and that's an F6 minus F5 divided by the spacing. F6 isn't stored, that's a problem, and so we'll have a boundary condition problem. Notice when we're taking derivatives of F, there is no boundary condition problem at the first point. So that's something kind of different with staggered grids. Boundary condition problems only arise at one side of the grid. All right, so now we write the finite difference equations associated with the derivative of G. That's our second finite difference equation, and we have 5 of those. And at the very first point, we're trying to calculate a derivative here, and so that would be G1 minus a G0 divided by the delta X. Well, the G0 doesn't exist. That's outside the grid. We need to handle this in some way, so that is a boundary condition. And so even this finite difference equation only has a boundary condition problem at one side of the grid and a different side of the grid than F. So file that away as something kind of interesting. Okay, so here's our 5 equations. Anytime we have a set of 5 equations, we can put that into matrix form. So we store our unknown functions in this column vector F. On the right-hand side of the equation, we have an A times this function G. And then the way we're doing our finite differences gets lumped into this matrix. Now notice this is no longer a symmetric matrix. We have negative ones running down the diagonal. We have positive ones in this upper diagonal, but we have nothing in this lower diagonal. So it's not a symmetric matrix anymore. And of course, we're dividing by delta X on the outside. So 2 diagonals, and it's no longer a symmetric matrix. So a little bit more compactly, we can lump this big matrix with the 1 over delta X and call that the derivative matrix operating on F. So we're storing that in the superscript. That's not to the power F. That's reminding us that's a derivative matrix that takes derivatives of F. We would not want to take derivatives of G using this derivative matrix. And the X down here is telling us which direction that derivative is happening. And then we store F and G in column vectors. A is just a constant. So here's our first matrix equation coming from our first finite difference equation written at all 5 points. Well, we do this again. We have these other finite difference equations. Oh, and by the way, back here, I use Dirichlet boundary conditions. So I just did not access F6. That would have a 1, out here. So that doesn't exist. I dropped it. There's no other terms here. So we're just using Dirichlet boundary conditions. Okay, back to G. So we have our 5 equations. We can put those into matrix form. And it looks very similar to the first, but our matrix still isn't symmetric, but it looks different than this matrix. That's due to the staggering. We now have positive ones going down the center diagonal, and our negative ones are going down the lower diagonal. Nothing in the upper diagonal. So it's still not a symmetric matrix. We have 2 diagonals. They're very easy to build, right? We just call SB diags twice. But these derivative matrices don't look the same, and that's due to the staggering, and we need separate derivative matrices, whether we're taking derivatives of F or G. And again here, I've just used Dirichlet boundary conditions. I just assumed G naught was 0. But many other boundary conditions are possible, just like we've discussed in previous lectures. So in a more compact form, we can now take this matrix and write it as dgx. So the G superscript is not to the G power. That's reminding us that this is a derivative matrix that operates on G. And then the X is telling us which direction that's operating in. And so G and F are column vectors, B is a constant. So here's our final matrix equation. We started with 2 analytical equations, and we ended up here with 2 matrix equations. And we went through all the finite difference stuff, but with practice, from here on, we can just jump immediately from our analytical equations to those analytical equations in matrix form. I've had so much practice now, I can look at these and literally just see the finite difference equations like this. And we don't explicitly have to touch finite differences anymore. Now, given those 2 equations, we have two options for solving them. Something different has to happen since we have two equations and not one. One is we can look at these two equations and put them into a 2x2 block matrix form and solve that simultaneously. And so we'll get a column vector of two column vectors F and G and get our solution all together. And for small problems, that works pretty well. Alternatively, what we can do, for example, let's solve this first equation for G, plug that expression for G in here. Now we have a single expression for F that we can manipulate into this form. So now we can solve this equation for F. Of course, we'll need some sort of excitation. That's another topic. But we can solve this equation for F. Once we have F, well, we had the equation that we originally had solved for G, and that's here. So given F, we can pre-multiply by our derivative matrix, divide by A, and we have G. So this is a really fast, simple thing to do. The main work is solving that first equation. And once we have F, we can then calculate G. I tend to solve things this way. I think that works better when we get to larger problems. For very small problems, this first one might even work a little bit quicker. But if it's small, speed probably isn't too much of an issue anyway. So those are our two options. Now, something really cool happened. On the previous slide, we had a dgx times a dfx. We are multiplying two first-order derivatives together to get a second-order derivative. We talked about this before. Remember, we multiplied together two first-order derivatives, and this is the answer we got. And this didn't work so well, right? Because we have to reach farther out into the grid to calculate that second-order derivative. So we decided, no, we're just going to build a second-order derivative. Well, what's happening here? So we said that's not good to do. What's happening now that we have a staggered grid? Well, let's multiply them together. Look at what we get. This is actually the correct matrix, other than some boundary condition things that may be going on. That's another topic. But this is a perfect matrix. 1 over delta x squared, and that's the expression that we would have for calculating a second order derivative. So that is sort of magical. And there's a term for these two things. Sometimes these are called left and right derivative matrices. And a left derivative matrix reaches to the left to calculate the finite difference, and the right derivative matrix reaches to the right to calculate the derivative matrix. And if we multiply a left and a right derivative matrix together, we get a correct second order derivative matrix. And that's really cool. So this works perfectly with staggered grids, another sort of magical thing for staggered grids. Here's something else really cool. It'll turn out these two derivative matrices are related. Let's stare at these long enough, and in our minds, let's transpose this matrix. So what we're going to be doing then essentially is swapping the diagonals. So we'll still have negative ones going down the center diagonal, but now we have positive ones going down this lower diagonal. That looks very much like this, just negative. So what if we transpose and then negative? We would get one derivative matrix from the other. And that's exactly what we do. So it turns out we only have to ever build one of those derivative matrices. We can calculate the other one immediately from it. Now notice I'm writing a Hermitian transpose, and it will turn out when we get to more advanced boundary conditions, we'll be putting complex numbers into these matrices, especially for like periodic boundary conditions and some other things. And so it turns out that'll generalize to a Hermitian transpose, which is a regular transpose, but then we take the complex conjugate of everything. But think of it as just a transpose and then negative, and we can calculate one derivative matrix from the other. That's really cool. So we only ever have to build one. Now, this does not work for all boundary conditions. It does work for Dirichlet boundary conditions, periodic, something called Floquet, which is another type of periodic boundary condition where we have to account for phase across the grid. Things I know that it doesn't work for, Newman boundary conditions. And there's probably other boundary conditions that this does not work for. So be cautious, but if you can exploit this, we can calculate one derivative matrix for the other. And oh boy, does that simplify the code. And I love that aspect of staggered grids. Some final notes here. In my experience with formulation, when I have a system of differential equations, I like to jump almost immediately to matrix form. I don't stay analytical and substitute one into the other and then simplify and then finally do the finite difference approximations, because typically you'll be left with one variable at the end. You won't exploit the staggering. You'll have to be calculating different types of derivative matrices, and it turns out uglier and it doesn't work as well. I like to jump to matrix form almost immediately. So, like for example, we had our two differential equations. We went to matrix form immediately. I did not substitute one into the other. We only did that after we jumped to matrix form, and we can exploit the magic of using staggered grids and staggered derivative matrices. So that's just some advice I have for you. When we have multiple functions, I never seem to have to ever calculate a second order derivative matrix, right? It's just first order derivative matrices, left and right derivative matrices, where I can multiply them together to get the second order derivative matrices. In fact, there's been times where people have approached me with a differential equation with second order derivatives, and there's multiple functions involved, and they ask me how to do it, and I always tell them I think there were steps before this. And that's where you need to do your finite difference approximations. And once you have your finite difference equations, then go ahead and substitute them into each other. And everything simplifies when you do that. So in my experience with multiple functions, it's very rare. In fact, I've never in my career had to make specifically a second order derivative matrix for staggered grids. It's always, I only had to build the first order and we just multiply them together. I am sure there's something out there that would require that to happen, but I have yet to come across it. For most boundary conditions, we can calculate one derivative matrix from the other. And not all boundary conditions, as we said, but this is hugely useful, and almost always I can do this. Now, there's other times in equations where we might have some function, a derivative, and then a derivative outside of that, and we're thinking, oh man, we got to do product rule and all kinds of crazy stuff here. We don't. In matrix form, we just jump straight to this, and that's it. We don't have to think about anything. It just handles everything automatically here. So these staggered grids are doing a lot of magical things for us, and they're absolutely wonderful to use. We just have to keep in mind the staggering and our different functions are at physically different points, even though they may be within the same cell. Let's tie this together with an example and even go through all the MATLAB code. Here is the setup for this example. We have two coupled differential equations, two unknowns, f and g, and we even have some boundary values, and we're in the interval from 1 to 10. How do we solve this? Well, before we get to MATLAB code, we had some work to do on paper. This is our formulation. So armed with derivative matrices and how we do the finite difference method, we can jump immediately from our analytical differential equations to our differential equations in matrix form. That's pretty easy. At this point, we would like to reduce this down to a single differential equation, either in terms of just f or just g. I'm going to choose to put this just in terms of f. So what I'll do is I'll take this first equation and solve it for g. Now later on, we're going to reuse this equation to calculate g from f. But right now we just have an expression for g in terms of f. Now what I can do is I can take this expression for g and plug it in here and have a single equation just in terms of f. So that's what's happening here. So I'm taking this equation, just writing it down here. I'm then replacing g with this expression. And so we end up with what's here in parentheses. Then I multiply everything out, and then I factor out this unknown f, and I'm left with a bunch of terms inside parentheses. Last step, I want to put that in its standard form, which is AF equals 0, and this is what A equals. We're multiplying two of our staggered derivative matrices together, plus 2 times the identity matrix. And with practice, going from these analytical equations to the standard form is very fast and easy. So we're done on paper. We didn't even really have to touch any finite differences. That is super cool. Let's go to the code now. So here's the implementation in MATLAB. So we start our program. We'll name it staggered grid. I guess I didn't have much of an imagination there. First thing I will do is initialize MATLAB. I will close all the figure windows, clear all the text from the command window, and then most important, clear all the variables from memory. And you know what? I might want to open up a figure window with a white background. And then I'm going to define everything about my problem. So I have a start point, an end point. I have my boundary values, and I'm choosing to put 1,000 points on this grid. Holy smokes, that's probably way more than I need, but this is such a small problem, I can get away with it, and I can be almost assured I'm going to get an extremely 10 times over converged answer. So we'll calculate the grid. Here's the grid spacing. So it's the span of the grid divided by 1 minus the number of points, right? Because 1 minus the number of points really gives me the number of cells in the grid. And so we divide the total width of the grid by the number of cells to get the cell spacing. Then we'll calculate the grid, and this is really the positions of the points across the grid, and this is really just for graphics purposes, so I'm not paying too much attention to what is there. We need to build our derivative matrices. So we'll take the approach where we build our derivative matrix for F, and then just calculate the derivative matrix for G from it. So this is how we do it. The first thing we'll do is we'll initialize it all to sparse numbers. So this is a nx by nx matrix, all of zeros, and it's sparse. Then I'm going to do 2 calls to spdiags. That's the built-in function in MATLAB that deals with sparse matrix diagonals. And so the first input argument is the data that I want to insert into the diagonal. So we're inserting an array of -1s. The second input argument is which diagonal we're inserting into. 0 is the center diagonal. So we're going to have a bunch of -1s down the center diagonal. And then the third input argument is the matrix that we want to insert the diagonal into, which is dfx, which is zeros right now. So we're going to come out almost with an identity matrix, just with -1s down the diagonal instead of +1s. Then into that same matrix, so this will retain those -1s down the center diagonal. Now down that upper diagonal, just above the center diagonal, we're going to insert +1s. That gives us our 2 diagonals. Then we'll take the whole thing and divide by delta x. That finishes our dfx derivative matrix. And then we calculate dgx from it as the negative Hermitian transpose. All real numbers in here, so the Hermitian part isn't doing anything right now. Onward in the MATLAB code. So now we need to build our matrix equation, at least the initial one before we put the boundary values in there. So we need the identity matrix. So SPI is the sparse identity matrix. And now we calculate our A matrix as dgx times dfx plus 2i. And this came from that formulation that we did on paper at the very beginning. And this is where I feel like I'm literally typing in the differential equation. It can't be solved right now because our equation is AF equals 0. And so we have to incorporate the boundary values. So, and sometimes this B I'll do up in this step, but we start off with a B that's zeros everywhere. We'll then go into the A matrix, and I've broken this into more steps than I really had to, but what I'm doing is I'm zeroing out that entire first row. I am making the diagonal element 1, and then I'm inserting my boundary value into B. And I'll do the same thing for the very last point. So the very last row in A, we zero out. We put a 1 in the diagonal position, and then we put the boundary value in B. We are now ready to solve our matrix equation. So the shortest is actually the longest. This is the most computationally intensive part and the shortest line of code, and MATLAB handles a lot for us right there. And we're solving A inverse B. And notice we're not actually calculating the inverse of A. That's a very bad thing to do. It's incredibly rare in linear algebra that we actually calculate the inverse of matrices. Not unheard of, just incredibly rare. So if you're ever doing that, triple, quadruple think yourself, because it's very likely you don't actually need to calculate a matrix inverse. A backward division is a much more efficient operation than calculating an inverse and then multiplying. Okay, once we have the answer for F, we'll go back to that original expression for G that we had, and this is the expression that we then substituted in to come up with one equation just in terms of F. Well, we can use this to calculate G from F. At this point, the problem's solved. So we may wish to visualize those results, and when we do that, and here's our answer. I've dressed it up a little bit. It looks like we're looking at sines and cosines of some sort with some kind of phase, which is another interesting thing I'll point out here. The finite difference method does not give us a symbolic answer, but sometimes it will suggest a symbolic answer. So I'm looking at this and I'm seeing that, hey, this is probably sines and cosines. So if I was ever asked to solve that initial set of equations by hand, I might do it first numerically because I'm lazy. It's a skill I have. And now I know, hey, sines and cosines is my answer. And so that gives me a clue maybe of how to go back and solve that by hand. And so that's another whole way we can use the finite difference method. But otherwise, we're just visualizing the results here, and I dressed up my graphics a little bit. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.